Okay, so one of the things about National Instruments' product line is we're very well known for test and measurement. And so we're typically known for being able to get real world hardware into the computer so that you can then do analysis on it. Well, with this additional multi-core and now GPU computing capabilities, now we can solve some really, really large problems that on the desktop just weren't doable before. And they're small enough so that if you looked at an HPC environment, you would say, oh, the communication overhead is too much, so you just throw them away. You wouldn't want to deal with them. And what's even more cool about this is that we can do it in a real-time sense. So now we can take on problems that were not just big for the desktop, but now can be done hardware in the loop and programmed with LabVIEW. So an example of that is we've now taken one of our computing problems that's related to the European Space Observatory, where they're making an extremely large telescope. It's going to be the largest telescope in the world, okay? They're designing and prototyping it at this time. And so we use LabVIEW to show how one of the mirrors, which is 40-meter wide, that's about half the size of a football field, okay? How that mirror can actually be controlled. Now, why does it need to be controlled? Well, it can't be made by one piece of glass. Instead, it's made up of these 984 mirror segments, and those guys are about 1.5 meters wide. Now, each one of these mirrors, to make a continuous surface, has to be controlled within about 10 nanometers, okay? So, if you take all of the sensors that are in the system, you get about 3,000 of them. And that tells you the placement of the mirrors, okay? You also have about 3,000 actuators, and those guys are actually controlling the pitch and so forth of the mirrors. Well, this 3K of sensor data and 3K of actuator data has to be controlled by some algorithms. We're using LabVIEW now to actually bring in that 3K of data, apply a really large matrix vector multiply, which is at the heart of the control algorithm, okay? And then send the actuator data back out again and do all of that, and we're targeting 1 millisecond. Now, of course, we haven't quite reached that yet, but we've shown at NI Week at our annual conference in August, we could actually do it with 2 octal core systems with real-time deterministic networking between the two in less than 2 milliseconds. And that's what's existing hardware and software today. Now, what I did is I took on that challenge and I said, I wonder if I can do that with one workstation and a GPU card. So that's exactly what we've shown here, that's showing in the Dell booth and in the NVIDIA booth, is we've shown how that same dual octal core system can now be done as a single octal core system using a new Tesla C1060 card. That loop on the Tesla, the matrix vector multiply, actually runs less than 3 milliseconds with the pre-canned CUDA-BLAS library that's available online. So immediately with one octal core system, we're actually able to model the same thing, hosting it, doing the mirror simulation, and doing the control, and we can do that just over 6 milliseconds.